Mm. Again, this week we were talking about population mean, and then we went over. We did say that this is try to help us to understand the population parameter. Now you use sample statistics to get an idea of the population parameter, the mean. That's what I meant. We talked about that last time. And then we say that it's the same idea just like before, just like the proportion. Yours it has to be random and so on. We take a go over, let me see, some of the formulas. This is the mean for the population mean, and it's the standard error for the population mean. Okay. Let's keep working. And then I think that's where we end up for talking about. We did an example, how to find the mean in the standard error. And then after that, I give an idea how that whenever the smaller, the higher the sample size, the closer it's gonna be, or the more accurate it's gonna be. That's what we spoke about. Okay. And so on. I see. I think we talk about some of the conditions and distribution. It's yeah, we did the same thing again. We also talk about the similarity theorem. So that and then we say we can use a start crunch or the TID4 to do to find the probabilities. Okay, and this one there wasn't really clear when I talk about it, but if you have the idea behind that, if something is not normal, once you use the central limit term, like whenever you have a sample size, you can have a normal shape. Okay, so I wasn't clear enough about this one. Like distribution that is uniform goes like this. So it's like it's a straight line, something like that. Okay. But if you use if you have a sample size n, if you're given a sample size n, and then this is large enough, then this sample size, the shape become a mound shape, just like this. Okay. And if you have a population that is binomial, then it becomes unimodal. Okay, bimodal. That's mean if the distribution is like this, bimodal like this, got two shape. But if you have an n for it, it becomes unimodal. That means you're gonna have the same thing here like that. Okay, if it's skewed to the left is skewed, or even right is skewed, doesn't matter. Sorry, oopsie. That's all about the shape. Then that's a left skewed. Then you have gonna be symmetric anyway. If there's no symmetry, you see, you're not having a symmetry anyway. Okay, whenever you have a sample size, whenever a sample size is large, if you have a large sample size, it's gonna the shape we follow a normal distribution table. I mean normal distribution shape, or it's gonna follow a bear shape. That's what I meant. Okay. This is chapter 9. Thank you for saying that. Okay, that's what I did last time. And then we spoke about, yeah, we did that an example, and then we start crunch and so on. Okay, another example, stuff like that. And we did say something about the t-distribution also. And I did say it's very easy to do it. I mean, whenever you have to use t or z, you will be able to do it whenever you look at cell crunch. Usually, if your sample size is small, let me talk about that right here. This is 9.3, and I'm going to be doing. Suppose you have a small sample size. If it's small, if n is small, okay? Usually this will happen. You're gonna have to use something called a t-distribution. You don't need to worry about that thing that much, but distribution, if you have a TI-83, it should be able to help you out basically. We talked about last time how to find the T. And if you have a large sample, all the time you can use the Z distribution or the Z distribution. Okay, so about the U, I'm trying to do my best. Distribution. So what does that mean? I know what we have. We say that remember what we said last time. Let me just show it to you quickly. If I can remember what we say, if you look at that picture we see right there, we have something like this. If N is very large, that's greater than 25, and then it's not normal. Then I'm going to use a different color here so you can see the differences. What you're going to have to do here is to use something called a Z distribution. Oops, sorry. Let's do blue. You're going to have to use Z right here. Okay. And also the next one, and it's large and it's normal. You see, you're going to have to use the Z distribution over here. Over there, and it's less than 25, that means it's a small size, and then it's normal. This is when you use the T distribution. Okay. And then the other one, if it's not normal, and then not, you have to something else. Okay. So let me remind you, not okay one, not okay. If N is small, when I put less than 25, it means small, okay? And then not normal. Not normal. Then you're gonna have to use something that's called non-parametric. Which we're not gonna do in this class. So whenever you say do that case, you're gonna say not, it cannot be used, okay? So everything that we do right here is called parametric. This is parametric. Let's see. So all of these three cases are for parametric. So in the case that N is small, and then it's normal, you're gonna have to do something called the T distribution. But this is what happened. Whenever the size is very large, sometimes I can use T. This is what happened. Whenever we have a large sample, and then it's not normal. I mean, if it's normal, if it's large, this is T and Z coincide together. That's mean they give the same values. Okay, but that's not a big issue. Oh, somebody's waiting room participants. No, okay. Okay, that's not a big issue. So you just remember these things. If it's very large and it's not normal, I'm gonna have to use Z. If it's very large and it's normal, I'm gonna have to use Z anyway. If it's small and then it's normal, I'm gonna have to use T distribution. Okay, so that's the thing we need to remember. You're gonna have this note after class today. Okay, so let me go back to here. Hold on, that's not the one I was using earlier today. I think I did whatever I was doing earlier. Okay, so let me just put it again. We have the T distribution here. Let's see. T distribution. I mistakenly erased everything I was doing today. T distribution. And then you can also have the Z distribution. And this is when N is small. Let's put N less than 20. And this is N is big. 25, my mistake, 25. 25, and then N is greater than equal than 25. And then in those cases, we assume that they are normal. Okay. These are assumed to be normal. So, okay, we're gonna say normal. Well, no, by normal, we mean that they have a bear shape. Oh, again, that thing keeps coming to me all the time now. Normal. Here we go. Okay. So the same pattern apply all the time for both cases. Okay. We can have the X bar. This is if we're doing a confidence interval, it's going to be plus or minus some margin of error. Okay. For both cases, it's going to be a X plus or minus some margin of error. Where does diverge? If you're using the t-distribution, then it's become X bar plus or minus some t value time the standard error. Okay, and this one will give you, if it's the z distribution, then be X bar. Oh man, X bar plus or minus some z the standard error, plus or minus z time the standard error. Okay.
I have a question.
Somebody have a question?
Yeah. So what is the formula trying to make? Like, what is it trying to figure out?
We try to do something called a confidence interval, just like we did for the probability. We just like we did for the proportion population.
And there's two different formulas for the T and then the Z distribution.
Yeah. If
Okay.
you have a small sample, large sample, then you use Z. If you have a small sample, you then use T. But the formula is the same. So what we did in the past, we had something for population proportion. We had P hat plus or minus E. Remember that? We did something like this. Then we did P hat times P, it can be P hat plus or minus Z value time the standard error. That's what we did in the past. Okay, so now we're doing the same thing for the population mean now. Okay.
Okay.
So and at the end, what we're gonna have, what it means is like you're gonna have X bar, wow, minus E minus X bar minus E less than mu less than X bar plus E. Something like that. But E will be different whether you use something like that. So now we're gonna be doing, let's do with the t-distribution. Whenever you do the t-distribution, you have something, because it's a small sample, there's something we need to do a small correction. The small correction is called a degree of freedom. Let me just show it to you. This is the one that we do for the t-distribution. Okay, it's like this. Whenever you do it, suppose you got 45 and it's 45. I know this is not a small sample, but we still can work on it. In that case, because this is 45 right here, we can either use the T or Z. We will not make any difference. But if they give you the T, the answer is kind of the same. Okay, the answer will be the same if either use Z or T, because this is a large sample, more than 25. But if I say Z, I may also something called degree of freedom. And then the degree of freedom, let me just remind you quickly what we spoke about last time. Let me see, what's the picture again? Right here. Last time we spoke about something called a degree of freedom. If your sample size is n is equal to 9, your degree of freedom will be 8. Okay, this is to account for the error because it's a small sample. Okay, that's mean we're not supposed to do the stuff for the small sample, because a small sample you have to do the t-distribution, then you have to account the error by doing something called a degree of freedom. So what we're gonna be doing here, we need to find the degree of freedom first. So I can see the degree of freedom for here, which is gonna be 44 or 45, take away 1. Okay, so take away 1, that's going to give you 44. So what we have here, this is the degree of freedom, and the value constant of the degree of freedom is 1.68. So this value, you don't need to focus, don't worry too much about them. You can calculate them using the TI-84. Okay, you can use the TI-84 to calculate it. I mean, Jacob, you have a question for me, Jacob? You want me to
Yeah,
go where?
it was just the slide before when you're writing the equations.
Okay, you want me to go back to it?
Yeah, please.
Okay. Here we go. And that's a Z, okay? That's not a 5, that's not a 3, that's a Z I'm trying to do. I have a bad way to do my Z. Sometimes I do it like this too, but
Good, thank
that's
you.
a Z. Okay, that's Z. All right then. Yes, this value is 1.68. Okay, it's very easy to, I mean, whenever you do the review, the TID4, which I don't have that inside my computer. I'm not able to show you the TID4, but in the homework they should show you, they show you how to do it. And as well on next week, whenever I come back next week, I can explain you how to get it using the stat crunch as well. Okay, but that value, even though, because this is a large sample, because it's 45, is close, that means Z will be the same value. Why is it close to this? It coming kind of quasi the same value. Okay, because this is 45, more than 25. So the next thing I'm going to be doing is to find the standard error. I remember to you about the standard error before. The formula for the standard error, it can be S over square root of N. Okay, so let me remind you that if you don't remember, do you guys remember the formula when I gave it to you last time? Right here. Let me just, I think that was too much here, too much writing here. So let's go all the way up here, right there. Did I write it down here too? Okay, so let's go even higher, right here. As you can see, this is the formula for the standard error is sigma over square root of N. This is what happened. Thing also can happen if sigma is unknown. You can use the standard deviation of the sample. The sample standard deviation. You can use the sample standard deviation. So as you can say, sigma, I mean, the new standard deviation, you can just let me put SE and say the new standard deviation will be, standard deviation will be the S, that's not a 5, that's another S, over square root of N. Okay, if the sigma is unknown. I think we spoke about it also last class. Let's see, going, see. What did we talk about again? I think we talk about right here. Right here. So we said the standard error for this will be like S over square root of N. We talked about that last class. This is when the sigma is unknown. So why not? Because we're dealing with a small sample. Okay, I know it doesn't, we don't know anything about the sample. That means sigma is assumed to be unknown. And then, so for that sample, you are able to get an average of 9 hours. That's the mean. This is going to be X bar right here. And then remember, this is from the 45 sample, and then that'll be the standard deviation. So therefore, this is not the one for the population because taken for on randomness. This is random sample. See that? That's a random sample I've been taken. From that random sample, you're able to generate the X value and the standard deviation. That's mean here in this case, you don't know anything about the population. You don't know anything about the mu either. Okay? You don't know anything. So what I'm trying to do is to try to get an idea about the mean. Okay? So whenever we do the same, using the formula above, so what we have X bar minus T time the standard error and that's going to give you 8.5. And then for the lower bound, and so on. That'll be the plus right here. Okay. So what we have now, it means that mu is a value that it can either be between 9.5 or 8.5. Based on that, that's mu is a value that feature between 9.5 or 8.5 and 8.5. So that's mean if you do a line like this is 8.5, and this is 9.5.
What does mu stand for it again?
Mu is the population mean.
Okay.
They're gonna be. I mean, this is what I'm trying to figure out. Mu can be anything between there. It can be between anything here. Okay. Is the one I try to calculate. It can be anything between 8.5 or 9.5. That's the population mean. Remember, here we're working for sample. This is a sample that is given to us. We know nothing about the population. Using that sample, we can have an idea about the population. Okay, you can have an idea about the population. So we assume that probably the mean is we're gonna have an exact value for the mean based on a number between 8.5 and 9.5. Okay, is actually I'm trying to I mean, if I can give a quick idea quickly, whenever a weekend is coming, we given the data, we can have an interval where it can hit. If the weekend is coming, okay, that's the weekend, for example, is coming, it can go either here. We can always have an idea where it can go. It can go or go down, something like that. Okay, we always have that margin, I mean that interval where it can go. If you look at whenever they give you the material, I mean they give you the online, whenever on the TV, whenever you can come and they say you can either hit either on top by Jacksonville or you can go down to Miami, or they can say, you know what, based on the data we have recently, you can either go into Miami or you can go to Key West, something like that. And then when it gets closer, oh, we say you're gonna go to Key West anyway, in the city of Key West. But we don't really have a specific city, but we can say it's going. I want Key West. Then you go. All right. So we can predict using numbers. We can predict information about the population. We can predict some stuff. I mean, we're gonna be our prediction will be 99%, something like that, or 95%. Okay. So it's not going to be 100%. That's what I'm trying to tell you. I remember one time I was even down in Miami. There was a weekend coming. Everybody was 99% sure that the weekend was going to hit exactly to the city of Miami. I mean, and which is in the southeast of Florida. Okay. And once the data keep coming, for some reason, that the interval switched down to Key West and went to the southwest area. So everybody who moved to the southwest area would get hit by the hurricane. So that's why I'm trying to tell you, with statistics, you can predict a bunch of things. With some degree of freedom or with some confidence. Okay, with some confidence. Okay, whenever you do a prediction, it's not going to be 100%, but it's going to be either 99% or 95% or something like that. Okay, you can say with 99% confidence, I'm confident that the hurricane will be hitting this place or we go in that place. So that's me sure about it. And that's why we're trying to understand with statistics. We're going to try to predict things that we cannot do. Again, just like I gave you the example previously, when I was saying that I'm from the islands, if I'm being rude to you, and then you find somebody else that from the same island who's been rude to you, and a third person on this side, you don't have to travel to that specific country and deduct that and conclude that everybody is rude. Based on your interaction with that small sample, you can we can predict or everybody in that city, on that specific country is bad or is something like that, is rude. You don't have to travel, but you based on your interaction with small people around that from that specific city or country, you can have an idea of the entire population. That's what we're doing here. We know nothing about the population, but based on what we have, we can predict things. Okay, so this is the interpretation here. As you can see, they give you 90% confidence interval. What I will say, we say we are 90%, 95%, 90% confident that the true value of the population mean is between 8.5 and 9.5. This is how we do it on the internet. And I'm going to write down for you. We can say we are 90% confident that the true value of the mean is within 8.5 and 9.5. If you do a study and find out the mean is beyond 9.5, it means that I underestimate. If you find that out that the mean is below 8.5, that's mean I overestimate. But overall, I estimated right. My estimation is between 8.5 and 9.5, something like that. So we can try to do another question the way the book does it. So that's mean this is the same question here. Okay, you say we are 90% confident that the population mean number of hours on homework for all college students is between 8.5 and 9.5, something like that. That's mean this is the interpretation. That's mean there are 10% of time, 10%, I'm not that confident. Okay, 10%, I won't be that confident. That's mean if my mistake, if I do a mistake, that's mean don't come and sue me, because I know I did say there's 10% for error and there's 90% of chance for accuracy. Okay, so we need to understand that. Any questions so far? Okay, so this is a attempt I just said earlier. This is the same question. Say we're gonna be 90% is gonna be okay, and 10% of the time we're gonna be wrong. Okay, that's just that you use it for you to read. Just read it through. Okay, so something like that. If you have to do this problem, because what we just did right now, we did use it using regular things. I mean, like one other thing that bother everybody, I know that the coffee time is 44, but if I don't get T, what will happen? I don't have T. Some people, it might be hard for you to get the T value, but if you use a stat crunch, either what do you call it again, the TID4, you can just plug in the values just like this. You say, for example, the simple mean was 9, the standard deviation was 2, the simple size was 45. Remember, you do stat, T statistics, one sample with summary. But the reason why I know that the sample is large is 45, but sometimes the problem might want you to do something like this. As you can see, look at the problem here. The sigma is not given. If the sigma is not given, it's best to use the T statistics. That's one thing I need to point out. I mean, just if sigma is not given, you have to put this. Let me just.
I have a question.
Yes.
So for the test, last test, when I tried to use StatCrunch, it wouldn't let me open up a window to pull up the StatCrunch. So how do we use StatCrunch during the tests?
How many of you didn't use StatCrunch? I think some of you used StatCrunch last time. Maybe you have some specific, I don't know what's going
Yeah,
on.
it's the honor logged. It blocked out everything on my computer, so it wouldn't let me pull up anything like
Which
StatCrunch.
one? What was like the last exam?
Yeah,
Exam
the
number
last
2?
exam. Yes.
I mean, I saw so many people did it. I don't know. We need to look at what's going on, okay? Did you get in touch with them?
No. I was kind of running out of time, so I didn't have time to like pull up the help button and all of that. So
Anyway, if you didn't do it, then contact it, because I already put the link for to use it. You understand? You're supposed to be using StatCrunch, or you can use a TI-84, just like it is given to you. And did you use a TI-84?
I had a graphing calculator, yeah.
Okay, then so use a TI-84 then if it's easier for you. Okay, but anyway, I need to see that what's going on. So okay, so we need to see that next time you do the test. So we can let me know, okay, right away.
Okay.
Okay. So I was saying, so I can add on this one, as you can see here, this is normal. So we can add to that formula here. On that side, on the left side, we can say sigma is unknown. We can add that to this one. For the left side, and for the right side, you can say sigma is known. Okay. So this one we use Z, this one we use T. Okay. Okay. So sigma is unknown, but just have to remember these terms. So let's go back to the thing, the homework we're doing right here. Where are you? Okay. So we're gonna have to do the T statistics, because sigma is not given to you. Even the example they say sigma is known, you must use the Z, because the answer will be slightly different. Okay, because you want to have a degree of freedom. So you want to click next. This is from StatCrunch. We're gonna argue that next time with you. So we do the confidence interval and you press calculate. Okay, and that's it. As you can see, just like we said before, the value is, the mu is between 8.49499. That's mu less than 9.5. Okay, so this, you got the same result. Here, because I'm doing StatCrunch, I don't need to worry about the real value for T. I don't know, I don't need to worry about it too much, but I can find it. That's why I show you next time. But I don't need to worry about that. And then if it was a Z, then I just have to put normal, okay? So that's why we need to remember. Okay? But I mean, sometimes whenever you do the problem, it might be hard for you to try to get all the value for T together. Then that will be easier. That we just use it the StatCrunch. All right. Any questions so far? Another example that I can work on. For example, here you are given a data set, like 11, or like that. They give you the data right here. Okay. So they say to find a 95% confidence interval. Okay. First of all, you're gonna type this value inside on StatCrunch, or you can use the TI-84, type them in. Then you do stat, T statistics, and one sample, and fit with data. Okay. Once you do it, you're gonna go there and then select confidence interval. You're gonna choose, because you have the sample here. This looks different. Okay. Probably selecting recovery time, and then put next, and then confidence put 95%, and then calculate. As you can see, there's only to remember what N is here. I know you can count it from the list, but you type it in, you can find it anyway. There's only to know T, and then it's very simple like this. Okay. and then you calculate it, and that should give you an answer right here. That's mean my mu will be between 5.95. Let's put 5.95. I'm sorry. $95 less than mu, less than 7.53. That means I'm 95% confident that the true value of the population mean is between 5.95 and 7.53. Even though I don't know the value, but I'm confident, 95% confident about it. That means 5% I'm not confident about it. Okay? 5% of that I'm not confident about it. Any questions so far? If no questions, so let's work in. And then again, this is the definition, we just talked about it. Population is recovery time was between 5 and something like that, or you can do that as well. We are confident that the value of recovery time is within that. That's the way to say it. That's been 95% of the time gonna be, that's gonna be true. 5% of the time I'm gonna be false. Okay, that's, I just leave that for you to read. Okay, now the same way we did for the population proportion last time, we did something called hypothesis listing, and now we come back to this one again. We're gonna be doing the exact same thing for this class, for mean. Okay, so we're gonna be doing the exact same thing for mean. So hypothesis testing for population mean. Last time we did for population proportion. The only thing you're gonna be doing here, we're gonna have the same thing. You're gonna have a HOA, HA. Okay, you're gonna need the alpha. By default, alpha will be 0.05. It's by default. If nothing is given to you, by default, alpha is 0.05. And if the same formula hold, okay, you're gonna have to compute the p-value and then compare the p-value of alpha. The same thing we say, if the p-value is greater than alpha, you reject it, you do not reject HO. If the p-value is less than alpha, if the p-value is less than alpha, you reject HO. If the p-value is bigger than alpha, you do not reject HO. Kind of the same concept. I don't know if you guys remember, but I can just quickly see before I do so. The only difference between the two here, you're gonna have HO, for example, and HA. So it is like this, and then 2 dots. This time you're gonna have mu. Okay. I can say, for example, mu is equal to that's HO right here. That's HA. Mu is equal to mu sub 0, something like that. I can say mu is less than mu sub 0. That's one case. Or I can do, and so on, because you got three cases, right? And you're gonna have like HO, HA, mu is equal to mu sub 0, and then mu is greater than mu sub 0. And then one of the last one, HO, HA, mu is equal to mu sub 0. And then mu is not equal to mu sub 0. Remember, the HA is only taken inequalities. For the top one, HO only take equalities. That's why I say for last class, whenever we're doing the probability, I mean the proportion, the population proportion. Now within the population mean, mu. Okay, so whenever you compare the alpha, you're gonna either reject or fail to reject HO. Okay, then you're gonna have the same thing with the previously. The same thing with the previously. That's mean if you remember the steps, you just have to look. I mean, if you don't remember the steps, I would suggest you to go and look at them on the last test. Not last test, on the last subject. Okay, whenever we're doing population proportion. Okay, so let me just show you a quick example quickly. This is an example. This one say Ford claims that is 2012 Focus gets 40 miles per gallon on the highway. Does your Focus MPG differ from 40 miles per gallon? Okay, that's the question. So here, this is what Ford claims. As you can see, what I can say, this is mu right here. Mu, you say, get that. Mu is equal to 40. This is a general idea. I don't know how to get it, something like that. But I can do something. I can have a sample size n is equal to 35. Out of this 35, I can try to work on that number, which is X bar. Okay. Okay, that'll be my X bar. Out of that because this is from a sample. See, randomly selected sample. We find out it was the X bar of 39.5. And then with standard deviation of 1.4. Okay. And then at this time here, the standard deviation is taken from the sample. I have a question for you. Is this one the standard deviation of the population, or this is the standard deviation of the sample?
The standard deviation of the 39.5.
Okay, that means is this for the sample or for the population?
Sample.
Okay, for the sample. Now, because this is for the sample, I'm gonna say S now. S for standard deviation is equal to 1.4. If you ask from the population, I would say sigma equal to. But this is not given to me. They don't say what sigma is. They don't say what they go to. That means I'm gonna assume this is unknown, because it's not given in the problem. If in the problem you say that it is known, even though I don't see it, I would assume the 1.4 is sigma, but they didn't say anything. Okay, so this is from the sample, because they say you chart your focus over 35. You got 35 selected items, cars, and then you find out that 39.5, and you find out that 1.4. Okay, that's why I figured out. So for this one, we need to build something called the hypothesis setting for it. So we're gonna have the hypothesis. So remember, the HO only accept the non-hypothesis. You're gonna have HO like this and HA. For focus say it is 40. That means my mu is equal to 40. It will be something like over here with the HO. And then HA will be the opposite. Because they say less or greater than. Okay? If you say less than, I put less than. If you say greater than, I put greater than. Okay, I will say mu not equal to 40. Wow, that thing keep coming into it still. And that's how I'm going to be working on it. So that's my hypothesis testing, my hypothesis. Okay. Then the things that I don't know, I need to find alpha, or it's not. I need to have alpha. Alpha is not given to me. If it's not given to you, it's always by default 0.05. Anytime alpha is not given to you in the problem, it's going to be by default 0.05. Okay. So because sigma is unknown, we're going to use the distribution, and then we're going to start quant to do the problem. This is not start quant. So we're going to
Can
use
you
the
go
formula.
back for a second? I'm
Okay,
sorry, I didn't
sorry.
finish writing notes. So.
Right here.
Thank you, I'm done.
Okay. Now, we can use start quants, but if you do it by hand, you have to use the centrality theorem formula that we spoke earlier about. So this is for we're talking about the last class. So let me remind you a little bit of that formula right here. You see that is x bar minus mu over s bar squared, and that was last class. And then after that, we find the value, we find the degree of freedom, etc. Okay. And then we talk about it a little bit more. So this is what we're going to be doing here. This is what the formula is about. Okay. So you got the t. Now the p-value is 0.04. How did you do that? So suppose you're doing by hand, how do we get the p-value? In fact, because this is a negative, I'm sorry. This is how you do it. That's gonna be gonna do p if you're using the also give you something for that. You're gonna say p, okay? And then that's gonna be you can say t less than negative 2.11. Okay. Now, because it's a two-tail, because you have let me just show it to you again right here. Because this is because you have that one right here, okay, you have to multiply the value by 2. So what we're going to be doing, you're going to multiply this one by 2. Hold on, I should say p-value. I would say, hold on, p-value is equal to 2 times p of t less than negative 2.11. Okay. So I know it might be a lot. Let me remind you where I talk about that thing, the 2-time value. So let me go back quickly to my notes. Sometimes it's best to go like this so you can remember. Let's see, where is that thing again? Where are you? Okay, that was the class we did before. Whenever we're doing the first time we're talking about, I will show it to you right after, okay? When we finish that class first, I will show you to where we get why did I say 2 times. I'm going to go back to the very previous class, which is chapter 8, so I can show you where we talk about it. Then that's why you do the formula, then that will give you 0.04. Okay. Now, 0.04 is very small compared to alpha. Alpha is bigger than it. Because alpha is bigger than that value, you have to say reject HO. Okay. So let me remind you what HO was about again. So let me just quickly erase that so I have to use the space because I just rewrite it again. So this is, I'll just see what I just put right here. So that's the same value. That's going to give you 0.04. Okay. So they remind you again what we have. We got HO, we got H1, mu was equal to 40, and mu was not equal to 40. So we say reject HO. What I'm going to be doing by rejecting HO, I'm going to cross out the HO. That means this is not good. That means I have evidence that this is different. Okay. So remember, that means I have evidence this is different because I say reject HO. Okay. That means there is statistical evidence that this is different. Okay. Based on my data. So Ford say that it is 40 miles per hour. apparently that claim and have evidence that they're telling the truth. That's what I mean. I do not have evidence that Ford's claim is true, okay, based on my data, okay? I do have evidence this is not equal to 40, okay? All right, but the thing is that the Ford claim was equal to 40 miles per gallon. But when I do my study, I found out that's not true. Okay, maybe they need to we do the study again, but I do not have evidence that Ford's claim is true. That will be this conclusion that you see, well, this thing right here that you see over there, this is for us statisticians. Okay, you're gonna say this is statistical receiving that evidence to conclude that your Ford focus on it get 40 miles per hour, miles per gallon on average. That's for us. But for the people that will understand, you have to go back to the claim, explain to them for the regular people. What does that mean? If you don't have, if you conclude that it does not get 40 miles per hour, that means if you conclude that it's different, okay? So that's why you have to answer this question right here. So that question, does your focus MG differ from 40 miles per gallon? You're gonna say yes, it differ. It's completely different what Ford was saying. So these are the type of terms that we use whenever you're in a courtroom. You have evidence that this person is guilty. You have evidence that person is not guilty, something like that. Okay. So the wording is very important. Okay, but you have to understand with that little thing I did right here, they put HO and H1. So that means if this one say reject HO, you cross it out, then this is the one that is good. So it must be different. You already make everything clear right here by just saying that. Any question about that? Okay, no question. Okay, so using start crunch now, we do the same thing. I just went over this thing already. Okay, so this is another example in which they use start crunch. Okay, look at the way they say. They say 150 minutes per week of exercise is recommended. Okay, do college student exercise more than 150 minutes per? That's mean this one say mu is equal to 150. Okay. This one say, is it more than? That's mu greater than 150. So this, I already have my HO and I already have my HA based on what I did earlier. This is the claim. That's the claim. Okay. So this is the claim right here. I would like to know whether I need to reject it or not. Okay. And I mean, I don't want to use that term right now because I don't want people to get confused. Let's just leave it the way it is so people don't get confused. This is what we have. Okay. So we're gonna do a study whether students do more than 150 per week. Let's see, based on that data. Okay, so we use StatCrunch. We did this. You already understand all of these Chinese things. I'm gonna skip most of them, and this is what we have. Okay, now let's interpret. As you can see here, your p-hat, your p-value is greater than alpha. What does that mean? So remember what we have earlier. We have HO, HA, mu is equal to 150. Wow. $150. And then mu not equal to 150. Notice that your p-value, or I have it here too. Anyway, your p-value is this one. P-value, that p-value at 0.0812. and alpha as 0.05. The p-value is bigger than alpha. It means that do not reject HO. Based on last class, okay? Okay, wow. Do not reject HO. Okay, that's mean if they do not reject HO, what does that mean? It means that the following thing, this is what I'm gonna be doing, is either one, okay? It's either one or the other. So this one, I'm gonna exit out. Okay, I'm gonna exit out. Okay. So I'm gonna exit one out. So that's mean if I exit one out, that means I do not have evidence that a student exercise more than 115 minutes per week. I do have evidence the average is 150, but I know that this is the question asked me, whether could a student do more than that? Okay. So if I reject, he said no reject, it just mean this one is good. That means I do not have evidence that we have that. Okay. So let's look at the way the beautiful term they use. Okay. So this one said there is statistically insufficient evidence to conclude the average college student exam more than 150 hours per week, something like that. Okay. And that's how I do the interpretation. Any questions? Still good? Okay. One last thing I want to show it to you quickly. This is sometimes they give you in the exam they might give you something like this. You have to plug it into yours. It's either TI-83, TI-84, or the star crunch, something like that. So it was R5.05, something like this. Then this one said this is a question. This one said is the mean temperature with really 98.6. So that's why they do a few people, they find a different temperature. Okay. And then they want to know whether it is 98.6. That's the question. This is the question why whether it's 98.6. Okay. This is the question. So if we find that it is different, then that's the problem. Okay. So they select 10 people. Okay. So 10 FE people, and if that's mean I have to see no matter what. Okay, so let's see. When I use start crunch, I know this is not, you can say this is close to normal. So we already said that this is not quick, kind of like that. So don't worry about it. So we did say that we need to use, because a small sample, we're gonna use T. So this is the big term, small sample use T, okay? Most of the exam, we're gonna be assume they normal, right? So this is what we have. We have a p-value is 0.1309, okay? So let's see. I don't want to mess up this one because just in case you have to read it again, I'm going to write it over here again. Got HO, HA. This is mu, not equal to 98.6. And then mu, wow. And then the other one is mu equal to 98.6. So as you can see here, the p-value 0.13 is bigger than alpha. It's bigger than alpha. That's mean do not reject HO. Okay. Do not reject HO. That means you have to cross out this one. Okay, but I want to point out something. As you can see, whenever you look at everybody and the sample, some people got 99. Some people got 99. Some people even got 97 or 96. So as you can see, not everybody, even though they're healthy, they don't really have 98.6. But does that mean that we can conclude that the mean is always 98.6? Because some people didn't have 98.6. Some people get 99. For me, for some people, 99 is a fever. 99.7 is like, oh my God. You understand? So is that a problem? Even though it's like that, we still can see that it's normal, okay? We don't have no evidence that it's different. I'm sorry, I'm just go back. Because we check HA, we have no evidence that it's different of that. That's mean on general, everybody is 98.6. Even though you find some people that are a little bit different, but it's gonna be 98.6, okay? So this is a conclusion right here. We cannot reject 98.6 as the population mean body temperature. So as you can see, people find a way to express the same idea with different way. Okay, so this is what to make everybody understand what we're talking about. But the idea is kind of the same. Okay, so 98.6 is the standard one, even though you got some people have different value, but 98.6 is kind of like the standard. All right. I'm gonna be stopping here. Next time we come, we're gonna be doing some of the review. I'm gonna be using StatCrunch every next week. Okay, and then yeah, so I think that concludes the lecture for this term. So what I'm going to be next week, going to be doing the review, look at the review together, the review they have online. I would suggest you to look at the video that I put for you that use the TI-84. I'm not able to get the license to get the TI-84 in my computer. I'm so sorry about it. If I had, I would have done the TI-84 and the StatCrunch. Usually in class, I do the TI-84 and the TI-83, and even using other type of calculators. But for now, I'm gonna have to do the StatCrunch for now, okay? And then if you have any question, please, you're welcome to ask me. But as of for now, I'm gonna stop 10 minutes before the time. Okay, so if you have any question, please welcome, ask me, and then class is over now.